number, and if the number is 1, then it is the inclusion principle. If it is 1, you get a 1, and otherwise you get 0. So it's a good way to count that. So what you are doing is you are summing n and m up to x, and then you are summing when d divides the GCD of mn of mu of d. This is the same thing. And now you are happy, you have sums, more sums, and so you are exchanging this, and you say this is the summation when d, well, since you are dividing x, you may assume that d is at most x. This is not too bad, mu of d. And then you are summing m and n such that n is divisible by d and m is divisible by d. So by the way, here it is the same sum even. So it is the sum when n is up to x of n congruent to 0 mod d of 1. And you do the same thing for m. And you can separate them. This is why this part is easy, because you can separate the value m and n. And of course, this is quite easy. Now you understand what it is. This is about x over d with a very good error term, which is a big O of 1. And this will tell you something which is essentially x squared over d squared. And you take the x squared out, and you are summing mu of d over d squared. And since it is convergent, it is the same thing if you go to infinity, and this is just the 6 over pi square that I was announcing. Okay, so this is this Folklore result. Good. Now, the point I would like to talk about, I think I have to start erasing, is something when, this will be the aim of the talk is to do something like that. I'm not going to look at independent m and n, but in some way to look at two sequences, un, n, for example, and another sequences will be f of n. And then what you are going to say is to start, what can you say when you are looking at that? So m is now a function of n. And you are asking this question. So of course, depending on what is f, you may have different results. If you take for f of n, which is n itself, then this does not occur very often. It will get 0. And if you take, for example, f of n is equal to 2n, then of course, no, it will be the same thing. But if you take f of n is n plus 1, for example, they will be always coprime, and you will get something like x. So what you would expect in good cases is something of the kind. According to f, you would expect something, a result of this type. This is in some cases. And if the constant you get is something like 6 over pi squared, you would say that the sequence n and f of n are in some way somewhat independent arithmetically. It is a way to measure how it is independent. So the first result in this direction was, I think, in 1953 by Watson, G.L. Watson, who considered the function f of n. So what I'm going to do is, indeed, f is maybe not an integral function. It would be easier to put it that way. So I will take f, a real valued function, and take the integral part. Okay, just take the integral part. And so what Watson was looking at is f of t is equal to alpha t, and alpha, oops, you are not going to see it, and alpha is irrational. So alpha irrational, and then he proved that you have the constant, which is 6 over pi squared. Okay? Then shortly later, it was studied by Lambeck and Moser, and they considered different functions which are slowly increasing. For example, something like f of t, which is n, which is t to the c, where c is less than 1. positive C less than 1. But they studied much more general functions which are slowly increasing. Not increasing as far as x, but f of t is little of t, something like that. And they get also something of the following with CF, which is 6 over pi square, or in the case of independence. And this has been taken then by Erdős, Lawrence. I'm not going to go further into this. And I was surprised to notice at the end of the last millennium, there have been some conference about the mathematics. I think the theme was the mathematics of Paul Erdős. And there was some proceedings of that, and there were also a list of questions raised by Erdős and around questions raised by Erdős. It was surprising. This was the question, what can you say if you take what we call Piatowski-Shapiro sequences, that is to say function f of t is t to the c for any t, for any c. And this is something, by the way, it was, then when was it? In 2002, that Delmer and I, we considered any c. So c is a real number. I don't know if you can read that. Yeah. C is a real number, but not an integer. And again, you have the independence. So it was no longer slowly increasing. And there have been generalization of that. I'm not quoting everything, but one interesting generalization was by Bergelson and Richter. And what they were looking at was something which was a generalization of that. In that they were taking several functions at the same time, f1 of n, blah, 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 fk of n. Then what you would expect, so of course with again this. So this time independence, the value 6 over pi squared, the zeta of 2, was just because we were considering 2 elements. You remember we had essentially this summation counting the number of elements in an arithmetic progression square, and this will be something like 2 power k, or k plus 1, if you have k here. And so what you would expect is this. And so they had some results. It is 1 over zeta of k plus 1 times x. And they did that for f1 fn fk, which are essentially functions with polynomial growth. So you may think of Piatowski-Shapiro sequence with different values of c. This is one possibility, but it was much more, it's going further than that, because it was also using essentially functions from Hardy fields. That is to say, functions which have nice derivative and nice behavior at infinity. Okay? So Bergelson and Richter were doing that. So, yeah, time is passing. But I want to say 2 things about that, 2 remarks. One remark is that in all those cases, essentially, you have always this n. And this n is quite important. And it is important, it is quite difficult to get rid of this n for two reasons. One first reason is that you remember we were saying that we were going t, when we reverse the summation, if one of the component is n, then when you want to check whether by the Möbius function whether this is 1, you have just to consider the d that divides all those values, and so d will be less than x. Okay, so this is one point, that on the size of d cannot be too large. If you have different values which are large, then this is open question, and there are interesting things to do, and this is, by the way, why I present it here, because there are a lot of things that are still open and quite interesting, and I think some of them should be quite tractable. Okay? So this is one point about the size of D. And another point also is that if you are counting now the number of n up to x, that at n is congruent to 0 mod D, then this is not a difficult question. If you are asking the n up to x for which summation m to x such that f of n is congruent to 0 mod D, this may be more difficult. Okay? So at least you are here in a good position, because with this factor, you know that D will not be too large, and you know that this question about the n, to say that n is congruent to 0 mod D is something which is easy to handle. You just write that n is equal to D times n, and m is up to x over D. Okay? So those are the two things. Now what about counting something like that? How do you do for that? So this also I want to make a remark about all this, everything that has been done, at least here. This is more general, because they are not at all using only t to the c, they are using a lot of different functions. How do you do to get this? Well, there's something. First of all, you have to understand what does it mean that a real number u is congruent to 0 mod D. Maybe there are too many things on the board which are of no interest for the time being. So this is the trivial one. It's okay, we mentioned it. How do you manage with this? To say that integral part of u is congruent to 0 mod D. Well, this will be the same thing as to say that the fractional part of u over D belongs to the interval 0, 1 over D. It's not too complicated. You write that this is between a multiple of D and a multiple of D plus 1, and then you divide by D, and then you say exactly that u over D up to an integer should be something in 0, 1 over D. So this is almost trivial, but it changes the point of view, and now you are saying, okay, to tackle this sum, it is a question of distribution mod 1, because the u you are going to look at just f of n, and so you are saying that this is in a given interval mod 1, and so for that you have Veil technology for that. So now Veil technology, you have different ways. It means that you are going to study trigonometric sums. So by Veil, you reduce that by summing n up to x. Of course, there may be more things. I am just looking at one single sum, which will be easy, but maybe. And so this will be exponential of 2 pi I f of n over d, h f of n over d. Okay, h being non-negative, non-negative or non-zero, essentially. This is the important point, non-zero integer. Okay. So of course you immediately see that what we are doing when we are saying about Gatteschi-Shapiro sequences, on where we are talking about Hardy fields, function in Hardy fields, you have good derivative, and so you can use van der Korput for getting cancellation here. Now the point is that there is also another difficulty, is that if you want to convert these sums into this question, to know the distribution, it's usually good to have something about the discrepancy. Now, discrepancy means that you have good cancellation here. And there is one difficulty here. I am in some way back to Watson, that if you take alpha, simply the function alpha n here, you have a difficulty because it will depend on the Diophantine properties of alpha. If alpha is a nice function, square root of 2, 1 plus square root of 5 over 2, then you are in very good condition, you have a very good cancellation. But if you have something like a Liouville number, you know that the sum is little o of x, but this is the only thing you know. You don't have anything specific, and so you cannot use this technology of Erdős-Turan to go there. So what I suggest also, if you are interested in this question, is definitely go to Bergelson and Richter paper and see that they have a question about the fact that alpha f1, fk are alpha 1, n2, and n, for example, alpha 2, n2, and so on, alpha k and k. And what they suggest is to say, okay, show that if alpha 1, alpha 2, alpha k are linearly independent, then you have the 1 over zeta of k plus 1 constant. And this is not known. Because we need always something stronger than that. We need to know something about this. Okay. So I started at 10. Yeah. Okay. So it's fine. Blah, 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 blah. Okay. So we were looking at something different with the Dermota and Müllner. So in some way I enter the real case, but this will be enough for the Michael Dermota, Clemens Müllner, and I, last year. Okay, we prove the following. Let C be in 1, 2. Then we have the following. For any h, there exists positive integer. There exists n. Indeed, infinitely many n is exactly equivalent, such that all the elements in NC, n plus 1C, n plus HC are pairwise co-prime. Okay, so this is something somewhat different, different question. So then this is the point that we don't have the function n nowhere. And if you have something which is larger than 2, we don't know what it is. This is why I want more to stress, maybe even more than on the result, to stress on the fact that it would be nice to show that you can extend this, of course not for the value 2. This would be a problem, but that if you take C, which is a bit larger than 2, between 2 and 2 plus some delta, can you have the same result? A priori, you would think that they are independent, and for any C, this should be true. The fact that there exist infinitely many. Okay? Infinitely many exist is the same thing, because since it is for any h, you can take them longer and longer, and so you have infinitely many. This is not a problem. Okay, and with the, what should I do? There is only white, or there is, you have color? No. Okay. Okay, I try to manage as I can. So we have some extension of that indeed here, so first of all, since we are with Piatowski-Shapiro sequences, we have good upper bounds for the trigonometric sums, and so we can do things explicitly, and we can even say how large is n compared to h. And you may even find n, let us say, is less than something which is exponential of some beta of c times h. You can go up to that point. There is no need to go very far to get such an n. You have something like that. Of course, beta c, you need to have some beta c here. It cannot be uniform, because if c is very close to 1, then at the beginning, your sequence, if c is really very small, this is just the sequence n plus 1 n plus h, and it is not correct. So definitely you need to have this, that beta c will be tending to infinity when c is tending to 1, and it will be tending to infinity when c is tending to 2 in the same way. But otherwise you have something which is quite nice. Okay. So now what we wanted to do in some way is to do, just in the case of one term, to go from, in some way, just Piatowski-Shapiro to something general. And this can be done, and this is a result that somewhere we are presenting with a joint result with Sunil Naik. And myself, and put a dagger, and I make a comment on the dagger. Charlie, I see you are laughing. Okay. Which says the following: let f be a function which is twice continuously differentiable over 1 infinity, and such that 1 f is decreasing, f double dash is decreasing and tends to 0 at infinity, and f dash is tending to infinity. Of course, it is increasing because this is not in the, because f double dash is definitely. Then you have the following, that for any h, there exists n such that all the elements f of n plus 1, f of n plus a, f is inside. Are pairwise co-prime. And this is all. So of course you don't have anything which is explicit. You cannot use the Erdős-Turan technology. You have to do things by hand. But in some way you can do things by hand, because if this function is tending to 0, then you have a very good control, step by step, of what is going on with the f prime, and you can just do it by putting your hands in the matter. So of course, don't expect anything like that. Okay? So, yeah, I have just 1 second. Maybe I give you some idea. So of course, this implies easily that the function f of x over x is tending to infinity, and that f of x is little o of x squared. So you are really in the situation, let us say, of Piatowski-Shapiro with a c between 1 and 2. Okay? They will satisfy that. This is easy to see. Now, how to prove that? I just want to give you one thing here. Yes, first of all, there is also something we can prove, but this is very easy, is that you cannot expect, you may have very long blocks in which no two elements are coprime. on the other way around, because you can find very long blocks in which all the elements are even. This is quite easy. This is an easy part to do. And here, there is just some intermediate step, maybe, which will tell you something. And I will stop after that and the last comment. So maybe to understand that it's not a complete black box, we take H, which is given, we write pH to be the product of the primes up to H. And then you have the following: if we have A, f of n is less than 1/3, okay. F prime of n is less than 1/3h. F double dash of n is less than 1/3h squared. So I will explain why you have this. F prime of n is congruent to 0 mod h, and f of n, f prime of n are co-prime, then this implies this. So what is the point about that? You understand that this shouldn't be too difficult to get those conditions, because you can see how they're increasing by little step, because you have a very good control of f double dash. So this should be possible, and this essentially means the following: the meaning of A implies that integral part of f of n plus h, when you look at Taylor, of course you think that it should be something like n plus h times f prime of n, and it is true even as regards integers. You have this relation. This is the aim of this condition, and you see that this condition is not too difficult to satisfy. Okay? And then you have arithmetics. And arithmetic, this, if you work a bit on that, and this relation is not too difficult neither to see that you have that. But what would be difficult is definitely, it's not h, it is pH. I need a bit more than h. But this is the most difficult part in some way. The proof is really in this proposition to prove that you have this. This is easy, and don't tell you much more. I said that I was going to make a comment about the dagger. May I? Shaoli? Okay. So, there was some preparation of a monograph according to some lectures that have been done here. By the way, with the frame of some Spark contract, which was very interesting one. And it has been submitted in this result by with Naik was included in this. And it has been submitted. Should I say the name of the, okay, to some publication, and as monograph, and it has been referred, it has been accepted, and it turns out that it seems that the series, for the time being, is suspended with up to I don't know what, and due to my old age, I am not going to wait for too long for that. So with Sunil, we decided to offer our result to you, to dedicate it to you, and to put it in the proceedings of the conference. So, happy birthday to you.
Questions for our speaker?
Yes, this is a,
That's because
so this is,
the set of n should be dense.
yes, and the density is something which is given by Laszlo Toth, because Laszlo Toth looked at this question for integers, what is the fact that they are co-prime or something like that, and this is a work in progress with Henrik, and although it's not completely written, I can say that the answer will be yes, about the density, and also there are another extension which is possible is to think of Bergelson and to put more than two terms, and this also is something we are, so this is done also with Sunil. We have to write it correctly, but this is not a problem. But then for the density, it may be more difficult.
So I have this paper of Bertelsen and Richter.
It is for your 60th birthday, by the way. Yeah.
So there are lots of other problems inside
Yes.
related to dynamic systems. And
Yeah.
I stress your remark what should be this paper.
Yes.
It's
Yes.
for research.
And so, and it is in the volume for the 60th birthday of of Robert. I should have said that, and you can read also all the book, by the way.
And third remark, your PhD Shapiro results remind me of very recent work with Manfred Madrich concerning such sequences with respect to the Monodie-Charpentier distributional measures.
Yeah.
So maybe this is also related, and
Yeah.
there is some space for
Yeah, we can talk about that, yes, sure, with pleasure. If I can reduce my Tichy number, I would be very happy.
Yeah, I wanted to ask, you have taken F1, F2, Fk basically all from the same family, right? T power C.
Yes, no, in
In that
Bergelston.
Begelson
No, in
Richter?
Bergelston and because they are also taking functions which are in Hardy fields. That is to say, functions which are nicely differentiable.
No, suppose I take F1
Okay.
T is T and F2 T is log T. What will happen?
So they have something that they are using Erdős to run, and for that they need to have something explicit. So you cannot be too close to a function. So I cannot tell you whether log T is fine or not. But
I see. Okay.
but they have some condition. You shouldn't be too close to a usual polynomial.
Ah, okay. Thank you.
Yes. Yeah, so Jama, you said your Kalyan and Srini number is 2. Rather, we would like to put it, our Desue number is 2. Thank you.
Hi. So the first thing that you wrote on the board is like if you take a function f,
Yeah.
then you defined a constant cf, right? So do we know what are the possible values that cf can take? Because 6 by pi square seems to occur a lot. And
Anything can be done.
so like given any real number, you have an example of an f where you have
Yes,
that cf.
I am pretty sure that if you look at some f of n, which is something which is rational, you see f of n which is rational, alpha n with alpha rational, then you can really figure out what should be the value.
Okay, but
I'm sure that
so will you get every real number in between 0 and 1? That's my question. I can see how you can get rationals.
yes, so you get rationals, but I think then you make some block construction or something like that to approximate. But it's interesting question. There is no answer, but I'm pretty sure that we can do it. So
Okay.
I can reduce your number. Or you can reduce your Desouillet number.
Of course,
It will be
of
easier
course,
for me to
yes.
formulate it.
Thank you.
Let me just make one comment here. You had the list of work related to this kind of a problem. This one I'm going to mention is of the type n f of n relatively prime, but not f of your type. R.R. Hall had a few 3 or 4 papers in Acta Arithmetica
Yeah.
in the 70s,
Yeah.
where I think he looked, in one paper, he looked at a class of additive functions, but then it's, so f of n is summation f of p, p dividing n, but f of p is a polynomial growth, but they're all integer valued functions. And then the probability that n and f of n are relatively prime is 6 over pi squared. And so some interesting techniques coming in there. And what was interesting was the class of additive functions that Hall considered did not include the simplest and the most fundamental of all additive functions, namely the number of prime factors. So Montgomery drew my attention to that, and I proved at that time that n and omega n relatively
Yeah.
prime is
Yeah,
6
yeah,
over
yeah,
pi
I
squared.
remember,
So this
yeah,
class
yeah,
of problems is
yeah.
really very interesting.
Yeah.
Thank you very much.
Okay.
So let's give a small token of appreciation to Professor.
Okay, thank you very much. Thank you.
Okay, so we have a break now.